So this is my second report on analysis of the SANS data that we took at NIST. These data are the data taken as a function of applied field, and so this was taken with the rather intermediate detector setting. The data don't reach to a small Q as we need, but we do still see some of the small Q behavior and also the medium Q behavior that I discussed last time. So this is just an example of the data, again on a log-log scale. This is about 003 in Q, and this is the what we called the bump in the previous YouTube video, and this is the bulge then here. So what you don't see is how these data decay as you approach Q, and then in some instances spike up. That's just not available in this detector setting. Nevertheless, what I'm going to do is I'm going to fit these data to a simpler model which contains just the Gaussian function and the Lorentzian function that we used last time. And since we don't really have the centroid pinned down very well in these data, what I'm going to do is I'm going to fix this value of that centroid of the Gaussian there, a sub 2, to be the value, sort of the average value of what we got for all the large scan, the full Q-scan data that I presented a couple of days ago. And also, I'm not going to vary the Gaussian width either. I'm going to use the average value. So this value of A2, the centroid, is 003. And the value I used, I constrained for the half width was 0015, and so that was obtained from the presentation that I gave to you a couple of days ago. So I'll fit then the amplitude of the Gaussian, the amplitude of the Lorentzian, and the half width of the Lorentzian to these data, and I'll do that as a function of applied field. So these are the first set of data. Now this is taken for sector 0. Sector 0, remember, means that Q, this is Q, is parallel to B, the applied field, which means that the magnetization that we're measuring is in a plane perpendicular to Q, so it would be like in this direction over here. So in the black symbols you see the data for the Gaussian amplitude A0 plotted as a function of applied field, and in that the black data correspond to the +1 Tesla cooling field data. The red curve are the results from the +5 Tesla cooling field, and so there's actually a quite dramatic difference between how field cooling is affecting this particular amplitude, and it's true also for the Lorentzian for sector 0, that in general the sector 0 data amplitudes are most affected by cooling field. Now the other point I want to make before I go on is if you look here at large applied field here, these values of the amplitude for the Gaussian are very small, and that will also be true. They're non-zero, but they are the smallest of all the sector settings. Okay, so now if you just keep watching that as I go to sector 45, you see it did increase a little bit. The amplitude is decreasing at the exchange bias field. I should also point out what these numbers are up here. I'll go back to the previous one. What I did was I just fitted a Gaussian function to the black and the red data separately to figure out where the centroid was. And so for +1 Tesla cooling field, the centroid of the black data is -1.9 Tesla, and for the red curve it's -1.8 Tesla. And then the data in parentheses is the RMS width of that Gaussian. Okay, so these are the data for sector 45. The amplitude of the Gaussian decreases. For sector 90, it decreases even further. But at this point, notice the amplitude here at large field actually increases each time. So we can go back to that here. Sector 0, 45, and 90. So there's a general increase as you go from sector 0 to sector 90 in the amplitude of that Gaussian function at the highest fields. Okay, so the next is the amplitude for the squared Lorentzian term. This is sector 0. I don't know if it's perhaps interesting. These are a little bit different than they were for the amplitude for the Gaussian function. And I think you're going to see the same behavior here, that as we go to higher, to larger sector numbers, the amplitude at the highest fields increases, while the amplitude at the exchange bias field decreases. Notice also that in this region here, for all the measurements, is relatively independent of field. So it could be that there is some information. Perhaps we could interpret that information as coming from dysprosium iron 2 domains, or at least domains that are pinned that don't respond to field. Of course, there could also be substrate SANS, but that wouldn't change with sector. Well, I wouldn't think it should change with sector setting, but that's something we can think about. This is sector 45 for the amplitude of the squared Gaussian, and sector 90. See, there's not very much difference here between the two cooling fields for this sector. This is true for the Gaussian function as well. And so now we'll look at the half-width. So this is actually the domain size in angstroms here as a function of applied field for sector 0. So you have the largest domains at the exchange bias field and the smallest domains at the higher fields. And I believe this doesn't change very much as we go from sector 0 to sector 45 and sector 90. Okay, but this peak did decrease. So again, at sector 90, there's not too much difference between the two cooling field protocols, whereas at sector 0, there is still a bit of a difference. So that's the presentation of these data for the B-scan data. So thank you.